We are now in introduction to machine foundation, almost towards the end of our foundation engineering course, and I have taken 2-3 lectures. Now I have planned 2-3 more, and today I will just discuss what we have stopped in the previous class. From there I will start, and in this you can see that we have discussed 4 different types of vibration analysis, that is free vibration and forced vibration. Under that it is undamped and this is damped, and here also similarly undamped and damped. Okay. So, we have done all the analysis: free vibration, damped and damped, undamped we have done, forced vibration, undamped we have done. Now, we are doing damped, and already I have discussed in the previous class also that if you have a forced damped vibration, that means you have a something system like this, and you have a spring and you have a dashpot, something like this, and this is the mass. And then if I write down the equation, if I consider a dynamic equilibrium of this mass, then there will be, if I give in displacement this direction, so the mass multiplied by acceleration will be in this direction, spring force k times x will be this direction, damping force c times x dot, that also will be in this direction, and force is acting here, suppose F t. And then if I draw the free body and consider the equilibrium in horizontal direction, then I will get this equation, that is the equation of motion for this system. Now, solution of this will be containing 2 parts, one is a complementary part, another is particular solution. Complementary part, how to get it? Actually, you have to put this equal to forcing function equal to 0, and then damped free vibration, the way we have done the solution, same solution will be there. Additionally, when force equal to this, then I will be do the particular solution, and these two together will be the total solution. But as I have mentioned that since because of the damping present in the system, that first part will be diminishing with after some time, and only it will give a steady state vibration because of this particular solution, and that solution I will come to the next slide. And F t can be of 2 types, as actually with a constant magnitude with the time variation and the f naught sin omega t. Another will be frequency dependent. This is a constant force, amplitude and rotating mass system. Frequency dependent means what? Actually, this is the suppose a eccentric mass rotating with respect to some point, then in that case, because of this frequency, that force will be m multiplied by E multiplied by omega square. This dynamic force is this much. So, that also will be varying with time sin omega t. So, forcing function can be of this or it can be of this type. So, depending upon these 2 types of forcing function, the solution also will be little different, but they are basically same. But once I will substitute this by substitute this one by this one, that way actually small change will be there. So, let me go to the next slide. So, that is the solution, actually general solution. You can see that u actually displacement amplitude, of course, sin omega t can be there here, but this is the maximum amplitude at a particular frequency. This is the maximum amplitude. So, displacement is maximum, that means if you have this, then this is the one, by this expression it is giving that one. Okay. Now, in this actually I can write this one as u over f naught by k equal to under root 1 minus omega square over omega whole square plus 2 d omega over omega n whole square. I can write this form, and this is actually non-dimensional. I can say something m, and this is the shown here m actually with the variation of omega over omega n, or omega over this is nothing but omega over omega n also. So, this variation is that when m variation of m with respect to the frequency ratio, and if you observe this, that at a lower frequency, you can see at a lower frequency with the variation of the damping, you can see amplitude near resonance. This is the resonance here actually ratio is 1. The resonance amplitude is very high, and with the increase of the damping, the resonance amplitude reducing. That is one thing. And at lower frequency, you can see whatever may be the damping, the amplitude is almost constant, close to this value. So, this is one observation for this is a constant force system when f naught by k. So, this from this plot we can see that with the increase of damping, that is this is the damping is increasing this direction, with the increase of damping amplitude is decreasing, or we can say with the decrease of damping amplitude will increase. And you can see that if it is a undamped system, the natural frequency will be under root k by m. That means omega n and omega over omega n equal to 1, it is supposed to be peak, but you can see the peak actually slightly before the 1 it is happening. You can see for this resonance here, for this resonance here, for this resonance maybe here. So, resonance is shifting left side. With the increase of damping, the resonance actually shifting towards left, and it is happening before natural frequency. Okay. The resonance is occurring at a frequency before natural frequency. That is one observation, that is actually not exactly at omega over omega n equal to 1 resonance will occur. Resonance will occur slightly before, and at lower frequency ratio that your amplitude will be almost same whatever may be the damping. So, these two important observation can be made from this diagram. And suppose I want to find out the amplitude at some frequency ratio, omega n is known, and I suppose my frequency is double the omega n. So, omega over omega n suppose 2. Then I want to find out that, then first I will find out this quantity, I will put omega over omega n equal to 2 or damping some value suppose 0.1, then I will get this value. This value multiplied by f naught by k will be your amplitude. So, that your amplitude will be u will be equal to f naught over k multiplied by magnification factor. Magnification factor is what? This value of this. So, need not actually, since it is a simple equation, need not use the graph, but one can, if I know the ratio of omega over omega n, then I can use this equation and find out the magnification factor, and then magnification factor multiplied by static displacement means what? Whatever constant force is there in the dynamic, that constant force if you statically apply, then what is the static displacement? That is nothing but f naught over k, and that f naught over k actually multiplied by magnification factor, that become the amplitude for the dynamic condition. So, okay. So, this is the way one can calculate. Similarly, for any damping value or any frequency ratio, one can find out the amplitude using this equation. But what observation we can do? Suppose I want to know at a very low frequency, then actually this I can assume almost close to static displacement itself. So, let me go to the next slide. When I will substitute f naught equal to m into e into omega square, then our previous equation was what was actually u over f naught by k equal to 1 over under root the same this expression, but here actually in this case it is becoming u over m e into e over m equal to omega over omega n whole square under root this same quantity, whatever this 1 minus omega square over omega n square whole square plus 2 d omega over omega n whole square. So, this is the so the magnification factor for constant force system and rotating mass system little different. You can see this is the thing added. Simply how it came? Simply I have substituted this f naught equal to this, and then I have simplified, then the expression become like this, and here instead of m naught by f naught over k, this become another quantity, that means eccentric mass into eccentricity divided by m. So, this actually, so that means if I know the frequency ratio suppose 2 and damping suppose 0.1, then what I will, if I want to find out the amplitude, then what I will do, I will put this one omega over ratio is 2 and damping of 0.1 in this equation. I will get, this is actually I can say m here, this is called m or MR actually rotating mass system. So, I will get MR. If I get this value, then your amplitude will be equal to MR multiplied by ME by M. That means, in the rotating mass system, what is the eccentric mass, that has to know, at what eccentricity it is rotating, that has to be known, and what is the mass of total vibrating mass, that has to be. So, this and this, what is the difference? Total vibrating mass means entire foundation machine together, and this ME means its eccentricity mass. Eccentric mass means what actually in the machine itself there may be a part, rotating part which is rotating. What is the amount? That is actually ME. So, ME into E, these two has to be known, and then total vibrating mass, that means footing and together, that has to be known. If I know this, and by calculating MR I can find out displacement. Another thing is that like that you have got the general equation, but if I simplify, that means I can maximize this equation, I what value what frequency, this is the with the variation of frequency, this is the expression, but if I want to find out at what frequency the amplitude will become maximum, you will find that omega over omega n equal to some ratio, some frequency ratio, and that frequency if you substitute, then you will see that u max will happen at your u max will be, or you can say u over let me clean and then do once again. If I do maximize, then we will see that u over ME over E or u max will be equal to, it will be simply 1 over 2 d under root 1 minus d square. So, for rotating mass system, this is the expression. Similarly, for constant mass system, u max divided by f naught over k will be equal to 1 over 2 d under root 1 minus d square. That means, at resonance, this is u max means displacement amplitude maximum, means it is at the resonance. That resonance point, what is the value? It is depending on only damping. So, you can see both for rotating mass system and constant force system, that your resonance is amplitude depends only on the damping value. And how we have done this one, that procedure I am not going actually, and but what frequency ratio this is becoming, I will show in the next slide, both for this and this. And so, from this figure actually again you have to observe a few things. You can see here that again with the increase of frequency ratio, you can see this is nothing but omega over omega n also. With the increase of frequency ratio, amplitude is increasing and it is reaching to a maximum value, which is called resonance, and again it is decreasing. And again with the increase of damping from this direction, you can see amplitude is decreasing. And third observation is what? Actually you can see at a very large frequency ratio, suppose 2 or 3 or even more, you can see that magnification factor approaching to a value, constant value. This magnification factor, this one, that means this is one u max by or not u max, u over ME into E over M, that is approaching to a constant value equal to 1. That means, at very high frequency ratio, previously for constant force system whatever we have observed, at a low frequency ratio, that means 1/10th or 1/20th of the natural frequency, then we have seen that initial portion of the response curve, irrespective of the damping, the value almost constant, that is nothing but equal to m naught over k. and whereas the rotating mass system, you can see at a large frequency ratio, where frequency ratio 2 or 3 or even more, there actually that response or magnification factor approaching to a constant value, which is equal to, you can see this is equal to 1. So, I can write that at frequency ratio when approaching to large, then your this amplitude, this value equal to 1, that is another observation. So, these two observations from two figures can be noted. Okay. So, with this, let me go to the next slide, which actually important and you have to remember. So, you can see here, as I have told you that I have written equation for this is the equation we have done actually m u double dot plus c z into c into u dot plus k multiplied by u equal to f t. I have written like this. This is a general equation of motion. Now, as I have told before that in the foundation there are 6 degrees of freedom will be there, actually 2 rocking, 2 horizontal, 1 vertical and 1 your torsion. So, this is the vertical equation. So, when it will be vertical motion, I can write the equation of motion like this. If it is a horizontal motion, I can write down the equation of motion like this. If it is a rocking motion, I can write the equation of motion like this. If it is a torsional motion, you can write down the equation of motion like this. And I have shown before also. And this one, of course, we have 2 equations can be there for rocking with this direction or with this direction, shorter direction and longer direction. So, 2 equation, 2 degrees of freedom here. Similarly, horizontal motion can be in this direction or can be in this direction. So, because of this 2, 2, 4, 5 and 6. So, the respective motion, if it is a rocking, if it is a torsion or if it is horizontal or vertical, are corresponding to that the equation of motion. Now, we can solve all the equation similar way. Only thing here actually these 2 cases mass was there, but here actually second moment of area for rocking motion and mass moment of area, mass moment actually moment of inertia for the torsional mode will be there. So, those things I will discuss later on what are the parameters, but if you learn only vertical motion, that may be enough at this stage, but if you have since the vibration can happen in all 3 or 4 directions or 5 6 directions. So, because of that I have just given the equation of motion. Solution procedure will be exactly same, only you have to replace some parameter, nothing else. Okay. So, now let me go to and as I have told you that that 2 solution I have shown for constant force system and rotating mass system, and you can see that the solution important things you have to remember that when the force is f naught sin omega t and when force equal to m e omega square by sin omega t, in that case resonance frequency will be over, will have omega n over resonance will occur at omega will be equal to this, or omega over omega n will be equal to 1 under root 1 minus d square, and whereas in this case omega over omega n will be 1 by under root 1 minus d square. So, that means the resonance occur, as I have told you that this is actually smaller than 1, is it not? That means at operating frequency less than natural frequency will resonance will occur for constant force system, but this one actually greater than 1. So, omega or operating frequency will be greater than natural frequency actually. Okay. So, that means we have shown constant force system that your if this is omega or omega n, then your natural frequency was something like this. Okay, and whereas constant for rotating mass system, if this is the one, then your natural frequency was something like this. So, resonance was here. So, that means for constant force system your resonance occur before the natural frequency, and whereas for rotating mass system your resonance occur after the natural frequency. When you cross the operating frequency cross the natural frequency, so the ratio is 1 over under root 1 minus d square, 1 by under root 1 minus d square, and here in the constant force system it is omega over equal to under root 1 minus d square. This is the difference you have to remember. This natural frequency ratio, this frequency ratio, if you substitute the general equation in this, then you will get at resonance. This is the expression we get, what I have shown already. So, this is the general solution for constant force system, this is for rotating mass system, general solution. Now, this frequency ratio, if I substitute in this, you are supposed to get the maximum amplitude, and that expression become like this for constant force system, and it become this for the rotating mass system. That means, I have already shown here, this is actually nothing but u max, this is nothing but u max, this is also u max. Okay. So, that means, if I want to find out resonant amplitude directly, if I know the damping, I will calculate this one and then multiply it by f naught by k, I will get resonant amplitude. Similarly, for rotating mass system, if I know the damping, then I will estimate this one, then I will multiply by this one, then I will get the resonance amplitude. So, this table actually one has to remember. That means, for constant force system, what is the frequency ratio where resonance have occurred, or what is the resonance frequency. That means, this omega is, this is the omega r will be equal to omega n times 1 minus d square, and that means, it will be less than omega this entire thing will be less than, this will be less than omega n. Similarly, here omega n equal to omega will be equal to omega n divided by 1 minus under root 1 minus d square, that means, it will be greater than omega n. So, these two things to be remembered, general solution this and this to be remembered, and once if you substitute this equation, and then your amplitude maximum or resonant amplitude will get from this expression, this to be remembered. So, this is kept in the tabular form. You can see, if I clean here, you can see this is the one important thing, this is one important thing, this is already repeatedly I have discussed, this is one, anyway you have to remember, and then finally, these two are resonance amplitude, and then what are the other things? Omega n is this, and damping equal C by C c, and C c equal to 2 root k m. This all those parameters are also to be remembered. This is very essential for dynamic analysis. Now, now let me quickly go to the requirement for foundation design for vibrating load. So, no vibration is done to the structure on which machine is housed. That means, if I put a machine over this foundation should not be damaged, or to the adjacent structure also. So, because of the vibration of that, the adjacent structure should not also be damaged. No damage is done to the machine itself. So, if I have if you allow excessive amplitude vibration, then because of the shaking vibration of these machine parts may go wrong. So, that also has to be prevented. Performance of the machine or the adjacent machine is not impaired. So, if you have excessive machine, then sometimes it may get shut down, or it may get some maintenance requirement, all those things happen because of the high amplitude vibration here. Nearby machine operation also may be affected, so that also has to be prevented. Next one, you can see that excessive repair and maintenance. So, if I do not design properly, then you may require excessive maintenance or repair cost, that has to be prevented. Performance and health of the worker is not impaired. That means what? If you allow too much of vibration in the system, then during vibration what will happen, that people working in the around surrounding places, they may not be, that environment may not be comfortable, or it may be a health hazard may occur. So, because of that, you have to follow all those things requirement. That means what amplitude one person can tolerate, you have to keep the amplitude in that level. So, that is another requirement. So, performance and health of the worker should not be impaired, and health and comfort of the surrounding people. Suppose there is a huge forging hammer and that creates lot of vibration, it goes to surrounding places. So, that also has to be done properly, so that the health and hazard health and comfort of the people, the surrounding area also should not be impaired. So, these are the actually qualitative, that means what you have to do while designing, that you have to prevent all those things. And how we can prevent? If you keep the amplitude within the acceptable limit, then only it can all can be prevented. Okay. So, and what is the general guideline? You can see here in this figure actually, if the amplitude is frequency is very high, we will be able to tolerate very less amplitude, whereas in the low frequency you can tolerate little higher frequency. Because of that variation of frequency, you can see frequency and displacement amplitude, there are different range of tolerance we have mentioned. See this, that if I keep the frequency and amplitude in such a way that not noticeable to person, that means in this actually very safe. If I can design within this zone, then it is very safe. Then you can see barely noticeable, that means your frequency and amplitude is in such a way kept that sometime it will be noticeable, that is also safe and easily noticeable to person. Now, if the frequency and amplitude is such that within this zone, then easily noticeable, that means people may feel. So, because of that you have to design, and there are different ranges are given, and you can see beyond this limit, if the amplitude become more than 0.05 and frequency become more than 2000, then that cannot be acceptable, actually that is not acceptable. So, this is the limit for where actually amplitude or frequency can be. So, this is one guideline given by Richard. And next, and you can see that it is given by the code actually for different types of machine, and the frequency range, that different amplitude is given. The code actually IS 2974 part 1 is given reciprocating machine, permissible amplitude is 0.2 millimeter, and IS 2974 part 2 it is given for hammer foundation, and for foundation block what should be the limiting amplitude, for anvil what is the limiting frequency. Similarly, IS 2974 part 3 and 4 rotary machine is given between speed less than 1500 rpm, then 0.2 mm. If it is between 1500 to 3000, then your this will be 0.4 to 0.6 millimeter, and if it is greater than 3000, then 0.2 to 0.3 millimeter amplitude can be permissible. So, these are all codal guidelines. So, you have to, while designing, you have to keep the amplitude within this, and if you keep this within this limit, most of the problem whatever I have said will be avoided in general. And another typical guideline is that you have to keep omega n, actually omega should be like this. Natural frequency, if this is natural frequency, you have to keep 0.5 omega, and this is the range actually you have to fix operating frequency this to this, and then omega n should be. So, that means you have like this, either if this is the one, either you design like this or you can design like this. So, either natural frequency will be here or here if the omega over n is here. And actually you can see that another two guideline is, if the operating frequency is very high, the natural frequency. So, operating frequency is very high means somewhere here, then you have to design the system something like that. So, natural frequency. So, that means it is under tuning, that means you have to design foundation in such a way natural frequency falls much below the operating frequency. And if the operating frequency is very low, suppose, and then suppose if the operating frequency is somewhere here, then you have to design the system in such a way like this, that means natural frequency here, that is called over tune. That means you have designed the foundation natural frequency in such a way that it is far away from the operating. This is operating, this is operating, here this is operating, and this is natural frequency. So, that is called over tune. So, what is over tune, what is under tune, under what case you will do under tune, what case you will do over tune, that is actually the through these 2 points it is mentioned. Okay. So, with this perhaps I will stop here. Thank you.